first of all, we need to make everything clear on our page. So I'm gonna write this code. Also close all. Yeah. Okay. First of all, we are gonna define some codes, explanation of the MATLAB codes. S and also T 0 and 1 divided by Fs 0.02 and also Fm equals to 1000. So what we have, Fc equals to I guess also M is cosinus is I remember 2 times P times Fm times T, so it will be like that. These all are our definitions. So signal definitions and initializations. In the first part of our code, the basic simulation parameters are defined, as I said. The sampling frequency is set to Fs and it's 100 kilohertz. The time vector is created for duration and 0.02 seconds. And the third one is the message signal frequency is chosen as FM and it's 1 kilohertz. And other parameter is Fc, the carrier frequency is selected as 10 kilohertz. And the last one is our message signal MT is generated as a cosine wave, yeah, as you know. Fs is 100 kilohertz. Fm, Fc, we define our parameters and we are going to continue with next step. Next step is gonna be our AM family modulation techniques, and actually first one is gonna be AM double sideband, which is called DCB-LC. So I'm gonna write this. Sideband, as we call DCB-LC, like that, and we are gonna define something again, and here in this part the modulation index Ka is equals to 0.8, controls the modulation lift. The carrier signal is multiplied with the message added term to produce conventional AM. So we are gonna define our K equals to, as I said, 0.8 and it should not be capital. 0.8 carrier equals to cosinus. As I said, it's gonna be cosinus with different parameters like p and ft. Is it right? Yes. And also the other parameter is am equals to 1 plus k times m, which is called message signal, and also carrier. So we make our first step, and we are gonna do second step, and it's gonna be AM DCBCS, which is called suppressed carrier. So I'm gonna write this code 2 here. 2. I'm sorry, my phone. AM DCBC and suppressed carrier, as I said. So in this case, the carrier is completely suppressed. The AM signal is obtained by simply multiplying the message signal with the carrier. We can call it ST equals to MT plus, not plus, sorry, MT times cosinus 2p f carrier t. So we are gonna write this code. It's gonna be DC and it's equal to carrier signal. So our code is gonna be like that. As I said, we have defined this code as a second step, yeah. So we are gonna continue to the next step, and next step is gonna be third one, and it's also AM signal sideband SSB using Hilbert transform, and the Hilbert transform of the message signal is compute to generate a quad rotate version of the message. Then the SSB signal is produced as a formula, and we are gonna define this formula. So I'm gonna write this code again, and third SSB using, as I said, Hilbert. So first definition is gonna be MH Hilbert and M, and also the other one is SSB equals to M point times again cosinus 2p 2 plus p plus not plus time, and fc times t, and continue with mh times, this is gonna be sinus 2 times p again times f carrier times t, which is called the time. So we have defined our third step, or we can also say the third step of AM modulation. So it will be like that, and also I'm gonna continue with the fourth step, and it's gonna be, let me write it. So the first one is envelope detector for AM. Fourth one is envelope detector for AM. So what are we gonna do in this code? So the envelope of the AM signal is detected using the Hilbert transform magnitude. So we are gonna use Hilbert again. So here n equals to EBS Hilbert and also AM. We make this code true. We need to true. Yeah, and we are gonna continue our fifth step. Yeah, and fifth one is coherent detector for AM DCBCS coherent detector for AM and is both both AM and DCB-SC signals are multiplied with the carrier again for demodulation. After multiplication, a low-pass filter removes the high-frequency components, recovering the original message signal. So we need to define some other parameters on the our step. So first one is gonna be hush. Sorry. AM equals to and the carrier, and second one is DCBS equals yeah, it's true, and again carrier. So we have defined AM and DCBC modulations in this step, and again we are gonna do something about low pass situation, and it's gonna be again like two different modulation. AM, first one is AM, and it's gonna be like low pass, and AM, and also and the last one is gonna be about DCB SG. Okay. It's equals to again low pass and it's true and 2000 and yes. So let's check these R codes. First one is true, second one is it's true, third one, and the last one is so yes, all of them are true. Just yeah, they're all are true. So we are gonna continue with FM family modulation techniques. We have already completed the AM modulation techniques in here. Space. We defined our parameters and we have made our AM modulation techniques. First one, second one, third, fourth, and the last one. So we are gonna continue with the FM family. So I'm gonna make a quick copy paste in here to make them separate like that, and for continue the next step I'm gonna make it same in here to make them separate. Yes, yeah, it's clear now. So we can continue with our next definitions, and first of all we are gonna define our kf, and it's gonna be equals to 50 like that, and true, yeah, it's true. So the next one is gonna be narrow band FM, and narrow band FM is modulated using by again SD equals to cosinus 2 times P times F carrier times T plus QF times message signal MT. QF is 50 in here, we have already defined it, so we are gonna make it clear with numbers in our code. So I'm gonna write this. I'm gonna continue with 6 to remember where was I. Narrow bands FM MBFM narrow bands it's equal to, so MBFM equals to cosinus 2 pi FC T and plus QF times message signal, and we're gonna continue with the next one, and next one is gonna be 7. Let me explain everything. Wide bands FM, and it's gonna be maybe FM. So in here wideband FM is it's actually obtained by integration the message signal before modulation. This produces large frequency deviation, is used in high quality communication systems such as FM radio. So I'm gonna write this code, and it's gonna be a bit different. FM FM equals to cosinus 2 times P times FC times T plus 10 times QF times some M divided by Fs. So as I said, in a normally conditions we need to use integral, like the situation that we have paper on our table, but in this code we are gonna define it like that. So I'm gonna continue with the next step, and next step is gonna be with direct integration, and we can call it direct integration method. And eighth one is FM with direct integration. So we are going to define this code to it's equals to, it's gonna be again dependent on cosinus, and the method explicitly applies numerical integration. It directly represented the physical behave FM generation. So we are gonna do cosinus again 2 times P times F carrier times T again times P times F carrier times T plus QF times and it's equal to this. And in this code, as you can see, we have a different words in here, and we represented the integral in this code, so we can write it like that. So I'm gonna continue with the last two step in the FM modulation, and FM demodulation using differential the envelope detection is gonna be our last second step. So I'm gonna write this code in here. So 9 is FM demodulation, and also we can add this code in here like that. So I'm gonna make everything clear now. So differential FM DI, so FM ABS Hilbert DFM. So let's check this one. So in here the FM signal is first differentiated. Since frequency variations appear as an amplitude changes after differentiation, the envelope detector recovers the original message signal. In here we make this. So we are going to continue with the last one, and last one is gonna be FM demodulation using zero crossing race. So I'm gonna write this code in short in here. So I'm gonna make the definition, and then I'm gonna explain why I make this definition, or why I write this code. Sign, and also FM, not N, FMDI, and it's gonna be close to 0, and then it will be divided by length of FMDI. So I'm gonna make this code clear like that. So zero crossing detection estimates the frequency of the FM signal by counting sign chains over time. The detected rate is proportional to the message signal. So we are gonna continue with the PM family modulation techniques, and to make something clear and separate them each other, I'm gonna write this in here as we did before, like that, and also like that. PM family modulation is also different parts in each. So we are gonna start with the definition of KP, and it's gonna be equals to 2, and then I'm gonna continue with the NPM, which is called narrowband phase modulation, NBPM. The narrowband PM is generated using again ST formula. It's equals to 2p f carrier times t plus KP times message signal. So I'm gonna make this definition in here, KP equals to 2, and also the first one is gonna be our 11 message narrow band PM. So we need to make this code clear, so I'm gonna write this definition. NBPM equals to cosinus, as I said, 2 times P times FC times T, and also KP times T. It's our first step, and let's check this code clear. Yeah, and it's true. Yeah, and the next one is gonna be wideband PM, and it has a different formula too, and wideband PM is generated using a larger phase deviation factor, as we can understand the name wideband. So it has a formula which is ST equals to cosinus 2p FCT plus 10 KP MT. So if I want to write this formula in here in my code, wideband PM equals to cosinus 2 times P times MC times T plus 10 times KP times, and last one is gonna be M. So M is our, as I said, message signal, and let's check this code. Yeah, it's clear. So I'm gonna continue with the next step. The next step is gonna be direct phase modulation, and direct phase modulation, the message signal is directly added as a phase shift to carrier. This is the most straightforward implementation of PM. So I'm gonna start with the name and direct phase modulation. So PM equals to, again, it depends on the cosinus signal, so 2 times P times Fc times T plus Kp times M. So let's check this one too, and I don't want to write this code wrong. If I make a mistake or do something wrong, we will not be able to see our graphics. And the last one is PM demodulation using differentiation and arctangents. So the 14th one is gonna be like PM demodulator, and I wanna make this clear too, so I'm gonna add this in here. So first definition is dpm, it's equal to diff pm. PM, yeah, it's correct. And PM demod, it's equal to 8 and 2 image, and again we are gonna use Hilbert and also dpm, and also we are gonna write this real Hilbert dpm. Now it's true, and the last one is our 14th. Yeah, and this is the most straightforward implementation of the PM. So I'm gonna check this all one more time. Give me a second. 41 is in here, so it's true, and I'm gonna continue with the next one. So in this part, before the final conclusion, 4 separate figures are generated, and first message signal, AM signal, and AM demodulated signal, and the second one DCB SG signal, it's correlated demodulation and SSB signal. Third one is what was it? AM FM, and also last one is PM. Yeah, MBFM wideband family and FM demodulated signal, and the fourth one is MBPM, again wideband PM. The last one is FM, and this one is PM, and PM demodulated signal. Each figure visually demonstrates modulation and demodulation in both time and record signal domains. So we are gonna I wanna separate again this part, so I'm gonna write this in here. So I'm gonna make this. We are gonna write our last parts to see all graphics that we have, and first one is gonna be like that. Let me explain. Figure and subplot 3, 1 and 1, and also plot, yeah, TM, and the title is message signal. So I'm gonna write this like 3 times, and there's a difference between second and third step, and there will be about titles, and second one is AM DCBLC, and last one is AM demodulated. So I'm gonna make it short, which is like related, and in here we need to change this, and I'm gonna make copy and make them paste them, make them clear the other ones like that. The first one is completed, and I wanna check them all one more time to make sure that this is clear. Yeah, it's clear and it's true, as you can see. So I'm gonna continue with the next one. Next one is again figure subplot and 3, 1 and 1, and plot T DCBSP, and title is gonna be DCBSG. So I'm gonna write this code 2 more times, and there will be different parts in plot and also subplot and the title. The second title is gonna be DCBSC demodulated, and the third one is gonna be SSB signal. Also subplot is gonna be different. Second one is gonna be 3, 1 and 2. Plot is gonna be T, COH and DCBC, and the last one is gonna have subplot 313 and plot TSSB. So I'm gonna make this code open in here. So I will make it like that. So I need what that, and the last ones are gonna be about like that, and I'm gonna continue with the other ones. Figure subplot plot 2, 1, 3, 1 and 1, and also plot T and BFM, and also title, which is called MBFM, and the second one is subplot and 2, 3, 1, 2 and plot T wideband FM, and the title is gonna be title is gonna be in here, wideband FM again, not again, narrowband FM and wideband FM, and the last one is subplot 313, and the plot FM and envelope, and the title is gonna be FM demodulated and demodulated. So I'm gonna check this one to here 311, yeah, 311 and demodulated, and also wideband, narrowband, envelope, FM demodulated. Yeah, everything is true. Yeah, I'm gonna continue with the next one, and it's gonna be the last one. So I'm gonna write this code in here. Subplot plot 311 plot, also plot T narrow band PM. I hope it will be true. Title MBN PM, and also the second one subplot 312, and also plot T wideband PM, and also the title is gonna be wideband PM, and last one is subplot 313, and the plot is gonna be PM demote, and the title is PM demodulated, so PM demodulated. So let's check this one, and here subplot yeah, and I'm gonna make a note in here. All AM, FM, and PM modulations and demodulations are completed, and I'm gonna make it right here. So I'm gonna write in Turkish AM PM and PM. Never mind. So will be like that then. But I just wanna be sure about my code. So let's check this one. Is it true or false? It says clear, close all, we close everything on this page. It was clear. I've created now, but if there was something on our page, this code will be cleared everything, and we make our definitions in here: time, f carrier, message signal, and am family, k 0.8 carrier, cosinus, it's a formula, and the other formula is BC. So make it like that. And here true and true, and also true. I was here. So Epsilon AM is true. Current detector for AM is true. FM with direct integration. Oh, sorry. It's true. Cosine is true. 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 I will pass here fast because I'm really sure in the last part maybe there will be a mistake in the first part, but the other parts are true. I'm really sure about that. And let's call this subplot, figure, subplot, PM delimited. So I'm gonna, what is this? Yeah, as we know that it's true. So let's run. Okay, save. So run. I guess there's a mistake, so I'm gonna copy all the code and make a new page. So in here, new script, and close it, and in here past, and also run. MATLAB drive, save. Here, so where is the problem? I actually don't know where is the problem, but there's a service problem here. So I'm gonna make here that again. So comment video, and delete everything. Delete. And new script. save. So there is no problem in here, but what's the problem?